So my presentation is about the math within Good Will Hunting. First, a summary of the movie. Good Will Hunting is around the character of Will Hunting, who is a janitor at the auspicious MIT Tech, and then he possesses extraordinary mathematical abilities, even though he has like no formal education. He was a high school dropout, I think, never went to college. He just took books from the library and learned off of that. And after he finishes his first problem on this blackboard, it kind of sends him down this track of being discovered by this MIT teacher, and then later being, bailed out of some issues he was in because he is like, he has self-destructive tendencies, and he tends to get into trouble a lot. So the MIT teacher kind of bails him out of it and makes sure he goes to a therapist and everything to help him reach his potential. But anyways, I chose to do the opening problem in this math clip. It's kind of blurry.
Mod fx squared dx. So please finish Percival by next time. I know many of you have this as undergraduates, but it won't hurt to brush up. Thank you, Stephen. I also put an advanced Fourier system on the main hallway chalkboard. I'm hoping that one of you might prove it by the end of the semester. Now, the person to do so will not only be in my good graces, but also go on to fame and fortune by having their accomplishment recorded and their name printed in the auspicious MIT Tech. Former winners include Nobel laureates, Fields Medal winners, renowned astrophysicists, and lowly MIT professors. Well, that's all. If you have any questions, I'm sure that Tom has the answers.
To go through all 4 steps of the problem on the board. So first was to find the adjacency matrix of A. So I found that matrix can represent graphs by the points between them. So this is 1 and 1, 1 and 2, 1 and 2, and then so on and so forth. And then this represents the number of walks or lines, pathways between the points. So as you can see, between 1 and 2 there is 1 walkway, so that's why that's there. And between 1 and 1 there's no thing looping back to it, so that would be 0. And then on between 3 and 2 you can see that there's 2 because there's 2 pathways that go through it. And then that's the matrix that would represent the graph on the board. And then the next problem is to find the matrix giving the number of 3-step walks. So to do this, you would have to multiply the matrices, which I found, it's actually pretty interesting. So you multiply the first of each row and each column and then you multiply the second and the third, and you add them all together to find the sum. And that's what this is. And then you move over to the next row to find this one, next row to find this one. And then if you wanted to find this one, you move to the second column and do that. So I just did that to find A of 2, and then I multiplied it again by A itself, A of 2 by A, to find A of 3. So this was the number of 3-step walks in the graph, and that's the matrices that represents it. And then after that, it asks to find the generating function for walks. So it actually can be found in a geometric series because A of n represents the matrix and then whatever number of walks you put in, and then this is the representation of the number of walks, and then you can put it into a geometric form, and then you take the limit of that as it goes to infinity, and you can find that it is 1 minus a is like this, but just without the n. And then if you use Cramer's rule to find the inverse matrix, you find that the inverse matrix is equal to the adjacency matrix over the determinant. I forgot the word is, but it's like when you, okay, I don't know how to explain it. I don't know how to explain this part to you, Mr. Kruger, because I
That's
have
all right.
a hard time
Yeah.
explaining it to myself.
Yeah, no, you're okay. You're okay.
Okay, so basically you just use Cramer's rule to find the inverse matrix, which this is the equation for that, which is basically n is just the matrices without the ith and the jth row, and then divided by this, which you then find that n is equal to just the same as this, but with the -1 to the I plus j, and then you can find that the inverse of m is equal to this equation.
Mm-hmm.
And then for like number 4, I forgot to write out the specific equation, but it asks you to find the number like this, but using the generating function to find I of 1 and j of 3. So you can see I plug 1 and 3 into the problems for I and j, and then you can find that the adjacency of the matrix for n is equal to 2z squared plus 2z to the third, while the detritus of m is equal to 4z to the fourth minus 2z to the third minus 7z squared plus 1, and then you can take out z to the first using the, what's it called?
Synthetic division.
Synthetic division to find the coefficients for the bottom row, and then so it's simplified down to this, and then you can put it into the function to find the Taylor series to find the starting coefficients of the series. So I just did this and I plugged in f of 0 to be 0, f prime of 0 to be 0, f double prime of 0 to be 4, and then you put 4 into the equation and you divide it by the 2 factorial, and then do the same for all of these, finding these and plugging them in, and then you can find that the Taylor series is equal to 2z squared plus 2z to the third plus 14z to the fourth, and so on and so forth, with this being the overall Taylor series like ending. And then as you can see in this clip, I know you can't see it very well. There's no big photos with him out of the way, but that was Will's answer on the board. And if you look and compare to it, all of my answers were the same, and so I know that I did it correctly. And then question